Right, so this is lecture number 13. So in the previous lecture, in the previous week, we talked about work and energy approach, and then we had a brief recap of the momentum and angular momentum and the idea of impulse. Okay, so today we will move forward, we'll move further to the next topic, which is a system of particles. So till now we've been talking about a single particle, or at max two particles when we wanted to talk about internal energy and similar concepts. So now we would want to talk about many particles, n particle systems, so that we can very quickly generalize to rigid bodies. The first thing we talked about for a single particle system was Newton's second law, that is force equals mass times acceleration. So let's see if I have a system which contains n number of particles, how can I write Newton's second law? Is there a way I can write it in a compact form? So let's say we have an imaginary boundary that contains the n particles. And what we'll do is we'll start with applying Newton's second law on individual particles, because that is all what we know till now. So we have the ith particle with a mass mi. It has many forces acting on it. The forces comprise of external forces, so that I'll denote by capital F. And so on. So I denotes the particle on which the force is acting, and 1, 2, 3 denote the different forces, external forces, just a number. And then we can have internal forces that are acting on this particle by the other particles in the same system. So that we'll denote by small f. The first subscript denotes the particle on which the force is acting, and the second subscript will denote the particle which applies this force, because it's an internal force. And so on. We can have many other forces depending on the situation. And when we apply the Newton's second law for this particle, So we add all the external forces acting on the ith particle. So that's the first summation. And then we add all the internal forces acting on the ith particle. That's the second summation. Of course, J cannot be equal to I because there is no meaning of F II. So there is no internal force by itself. And this sum of all the forces acting on the ith particle is equal to the mass of the ith particle times its own acceleration. This AI, since we have the position vector written here, so this can be written as the second derivative of Ri. Now what we do is, we will write a similar equation for all the particles. In fact, since I have kept the equation for an index I, the index I can vary from 1 to n. So that gives me n equations for the n different particles, and I can add them all. So when we do that, when we add all the forces, the first summation so we will say that this sum is equal to simply Fi. So Fi denotes the sum of external forces on the ith particle. That's a notation I am introducing here. So this allows me to write this as this. So now I can add the external forces on all the particles. This is to avoid the double summation here. In the second case, I have simply kept a double summation. So earlier we had a summation of all the internal forces on one particle. Now since we have added everything, so this is the sum of internal forces for all the particles added together. On the right hand side, you also get a summation. So what is this term? This is the sum of all the internal forces. So if you look at the summations, you will see that you will have, for example, F13 and also F31. They are both added together, and we know that F13 is equal to negative of F31 because they are internal forces, Newton's third law. So we will see that the terms will appear in pairs, and when added together, the terms in the pairs will give a 0. If you expand this, you can easily see that this term becomes 0, or we can simply say the sum of all internal forces is 0. So, further simplifying the notation, capital F denotes the sum of all external forces acting on all the particles in the system, and this is equal to I have taken the derivative outside because right now we are assuming that the masses are not changing. The next lecture, we will see that what happens if the masses start to change. That is when we talk about rocket science. But till now, we are assuming that the mass is not changing. So derivative of mass with respect to time for any mass is going to be 0. So this is allowed. Oh, sorry for that. Yeah, thank you. And what is this? Anybody remembers? This is how we define the center of mass. So this becomes the total mass m times the position of the center of mass. That's the definition of center of mass. Till now we are talking about discrete particles, so we are taking a summation here. Is that clear? Or we can write this if you look at the second form, what that tells us, for a system of particles, the net external force or the sum of all the external forces acting on all the particles is equal to the overall mass of the system, that is the sum of all the masses, times the acceleration of the center of mass. So let's write it as acceleration of the center of mass. We knew this, but it was worth writing this again. Now, let's remember that center of mass is not a particle. It's a mathematical concept. Sometimes it gets confusing when we work with problems that we try to look for what particle is moving. It may happen that all the particles in a system are moving, but the center of mass may still be stationary. It may happen that all the particles are accelerating in addition to just a motion, and the center of mass is still stationary. No acceleration, no velocity, no displacement. It can happen depending on the situation. It may not be the case as well. Okay? So let's remember that center of mass is a mathematical concept. You can locate it, and if you know the motion of every particle, you can figure out the motion of the center of mass through the same idea. You differentiate the position of center of mass, you get velocity of center of mass. So velocity of center of mass simply the first time derivative of position of center of mass. Again, it may not be a physical point, but depending on how the other particles are moving, we can find how the center of mass is moving. Let's do a quick recap problem. So we have two particles, A and B, of masses m and 2m respectively, and the distance between them is d, separated by a distance d. A has some positive charge and B has some negative charge. Now what will happen, initially their velocities are 0. You're holding the particles, now you leave the particles at t equal to 0, they will accelerate towards each other and they will eventually collide. We want to find at what point will they collide. Can you tell me quickly? You can use the equation, the idea we just discussed. So see what the total force, external force on the system is. 0. There's only internal forces acting which are equal and opposite. So that means I can apply Newton's second law for a system. So that means the acceleration of center of mass is 0. Now the velocities to start with were 0. I mean velocity of center of velocity of the particles. So that means the velocity of center of mass was also 0 at t equal to 0. So since acceleration of center of mass is always 0, that means the center of mass does not move, and since the particles will ultimately collide, they will meet at that point. So what is the center of mass here? Position. Let's take this as the origin, the first particle. So 2 by 3, that is here. That's closer to the heavier particle that is expected. So this is where the particles will collide. So our next approach was work and energy. So we said that in certain situations, the idea of work energy theorem becomes more comfortable as compared to applying Newton's second law. So let's apply that for a system of particles. Now we already know that because we described the idea of work and energy for two particles when we are talking about potential energy. So we can use the same idea here. So the different kinds of forces acting on any system in this case can be internal and external. So we said that from work energy theorem for a system of two particles, but now we are generalizing that the sum of the work done by internal and external forces is equal to the change in kinetic energy of the system. I'll tell you what the kinetic energy of the system means, but for now we are applying this because we have applied this to an n particle system. Now the internal forces are of two types. They can either be conservative or non-conservative. So the sum of all the work done by all the different kinds of forces is equal to the change in kinetic energy. That's the work energy theorem. But we also learned that we can take the effect of conservative forces as potential energy. That is much more comfortable because then we don't have to find out or integrate the conservative force over a complicated path. It's better to work with potential energy. So we use this form of the work energy theorem for a system of particles. Right? That's pretty much it. So that's how you apply the work energy theorem or the work and energy ideas for a system of n particles. Now the next thing is, what is the meaning of kinetic energy in this case? Because we have many particles. Kinetic energy is given as, for a whole system, so we add the kinetic energy for all the individual particles. So we define a vector rho I from the center of mass g to the individual particle mi. Now we know that Vi squared is simply the dot product between the vector Vi. So Vi denotes the derivative of Ri. Ri is the position vector with respect to a fixed origin. Now what we want to do is we want to work with the center of mass in this case, because the particle by itself may be moving. So it's difficult to find the individual locations of particles with respect to the origin O. Sometimes it's easier to locate everything with respect to the center of mass. So Vi can be written as V center of mass plus the time derivative of vector rho I. Simply expanded the dot product. So we get three terms. So let's look at term number 1. So that's the kinetic energy because of the motion of the center of mass. Think of it as a disk that you have thrown. Center of mass is traveling, so the center of mass has a velocity, which is of course, I mean, it's a mathematical idea, but the whole center of mass of the system is moving, and the system may also be moving around the center of mass. This may be rotating or something else. Well, rotating is what we're talking about. So this is simply talking about the motion of the center of mass. How fast are all the particles moving as a system? Number 3. So this is, so rho I dot denotes the velocity with respect to center of mass. You can think of it as 3 balls. Connect them with some light string and you throw them. So they may together be moving with a large velocity, so that is number 1. And number 3 denotes how are they moving with respect to the center of mass. They may be moving with respect to center of mass as well. So that is what is this number 3. Is this clear? So for number 2, I will take VCM outside the summation because it has nothing to do with the summation over the number of particles. What is term number 2? What does MIRI give you? Summation MIRI. That gives the position of the center of mass. Now let's say your origin was fixed at G and you were measuring the position of each and every particle from G. That will be Mi rho I if you're trying to find the center of mass. But the center of mass is at G. That means it is 0. In the work energy theorem, if we apply it to a system of n particles, this is how we write the kinetic energy. Term 1 is the kinetic energy because of the motion of the system as a whole. Okay. Now you try to find the center of mass from G as the origin. You'll see that. Because when finding center of mass, the origin is of our choice. Whatever choice we take, we'll get the center of mass coordinates with respect to that chosen origin. So if you choose G as the center, G as the origin, by chance you chose that, then you will see that G is the origin. And this should give you, Mi rho I should give you the coordinates of center of mass. From the origin, it's on the origin, so that's 0. Our next approach was the momentum approach. So again, there is a mix of external and internal forces acting on any particle, let's say Mi. And the momentum, linear momentum of the ith particle. Given as this, MIVI, we already know that. If I apply the Newton's second law, or in the linear momentum form that we had discussed, the time rate change of the linear momentum of that particle is equal to the net force or the overall force acting on the ith particle. So we add this, add equation number 1 for all the particles. We get the total external force acting on the system is equal to the sum of the linear momenta of all the particles. Oh, sorry, sum of the rate of change, time rate of change of the linear momenta of all the particles. But this is not very interesting. It's not, I mean, we're simply adding the dpi by dt and making that equal to f. We want to understand if there is an idea or a concept of a linear momentum of the system as a whole. Can we define something interesting there? So we want to convert this to potentially a form that looks like d by dt of p of the complete system. Then we have a nice analogy between the Newton's second law written in the momentum form for particle as well as for a system. Let's see if we can do that. So this we do not know right now. Okay? So we're trying to see if we can write that. So what is the total momentum of a system? The sum of the contribution of the momentum from the individual particles. So that's MIVI added over all the particles. If we draw the same figure again, in the first term, VCM can be taken outside the summation. So what we get is the total mass of the system times the velocity of the center of mass. What about the second term? We already saw that this term was 0. What we see is the momentum, linear momentum of the system, which is the sum of the momenta of all the individual particles, can be written as the total mass of the system times the velocity of the center of mass. And that is exactly what we wanted. So we wanted to write this summation of all the individual momenta. So this can be written as m times velocity of the center of mass. Is that clear? Now this is going to be the tricky part, the trickiest part of all the cases, because now is when the things will get interesting. Because that is what is really interesting in rigid bodies. It's not the motion of the center of mass. I mean, that is also useful, but what's interesting is the motion of particles around the center of mass or around a certain point in space. So let's pay attention here to the ideas of angular momentum for a system of particles. So there are different ways or different points around which we can calculate angular momentum for a system. And if you had done the problem I had given you for a conical pendulum to find the linear momentum about different point, angular momentum at different point, you would have seen that angular momentum changes if you change the point around which you are calculating it. If that is the case for a single particle, that's also the case for a system of particles. That is what we learn through problem solving as to what is the best point to choose when calculating angular momentum about it. So we'll see what the expression is for different situations. So we'll take three cases. The first one is a fixed point O. That is, the point is not moving. The second case is about center of mass. That's also a very good choice of calculating angular momentum. That is the center of mass. Now the center of mass may be accelerating. It's not a fixed point. We just saw the center of mass can move if there's a net force acting, a net external force acting on the system. And the third one would be a general point which may be accelerating, but that is not the center of mass. Okay? So we'll start with the simplest case, that is the fixed point O. Now you may notice that this is something new, in the sense you may not have learned this during JEE. So the total angular momentum of a system about a fixed point O is simply the sum of the angular momenta that is contributed by the individual particles. So the angular momentum about point O for a single particle is the moment of the linear momentum That's how we write the angular momentum of a system of particles about a fixed point O. Now let's differentiate that with respect to time, because we studied that angular momentum by itself is nothing, there's nothing natural about it. The reason we study this because it leads to a very nice dynamical relation between the torque or the moment of forces and the time rate of change of angular momentum. So we are trying to see if we can get a similar dynamical equation for a system as a whole, as we have obtained for other relations such as Newton's second law, written in both the acceleration or the momentum form or the work energy theorem, and similar idea if we can use in a similar for angular momentum. We are trying to find a torque equal dl by dt if that exists for a system. So let's write dl by dt. So what is this term? Can you see how this is 0? dRi by dt is Vi, and Vi cross Vi is 0. Now Mi times Ai is simply the net force acting on the particle I. We will write this as the sum of capital F's on I and sum of small f's on I. this is equal to the moment of the external forces, well, the sum of all those moments, and the moments of the internal forces. But we don't like internal forces contributing towards moments. Can we see how the second term is 0? Let me show you this relation for a system of, because internal forces appear in pairs. So we have to see how they cancel each other. Now forces cancelling each other is simple to see from Newton's third law. But these moments cancelling is a bit tricky because Ri is different for different particles. Whereas Fi, when it acts equal and opposite, it acts on different particles. So let's see. Let's say you have two particles, 1 and 2, and the force that acts on 1 by 2 is F12, and the force that is applied by 1 on 2 is F21. This is the origin somewhere. So we have R1, R2. So if I was simply looking at, we are looking at this second summation. So we'll have, basically you can take all the internal forces and then find out the moment of that depending on where it is acting. So let's look at these two contributions. So the first one is R1 cross F12, and the second one is R2 cross F21. So we're trying to find out those moment terms where you have F12 and F21. There may be other forces as well, but we'll consider them as pairs separately. So this you can see, this becomes R1 minus R2 times F12. We apply Newton's third law, F12 is equal to F21 with a negative sign. And R1 minus R2 is simply, this vector can we see R12 cross F12 is 0? They're in the same direction. Internal forces act from one particle to the other. Central force, they are central forces, center to center. And so is R12, center to center. So two vectors pointing in the same direction crossed give 0. And now you can see, because internal forces appear in pairs, you can use the same idea and see that the overall sum that we have written above is 0. Direction of R1 should be reversed. So written R1 minus R2 is equal to R12, and from this figure I see R2 plus R12 is equal to R1. Correct. I may have used a wrong convention that you usually use. You can call it R21, whatever your convention is. So my R12 means it's a vector pointing from 2 to 1. But vectorially it is matching. So what we see is, let's summarize it. The time rate change of angular momentum of the system about point O, which is the fixed point, is equal to the summation of the torques of external forces about point O that clear? So we'll have to stop here because if I start with the next topic, it will take some time. So next was center of mass. Now, by the way, some announcements are due. So I have been a bit slow in uploading lecture material. I apologize for that. So I'll upload the lecture material, whatever is pending by today. I also have to upload 2 videos, I have to record and upload them. So that is also something I'll try to finish by today. So by today evening, you should get 2 videos which include problem solving from the previous lectures, as well as the remaining lecture notes. I just lost my pen drive, just found it here. So I'll upload that today. Okay? Anything else that you want to ask? We'll meet on Wednesday. Thank you.